Okay, let's go ahead and start the additional practice for the acids bases chapter. This is going to be a long video because there's 36 examples, and I'm going to try to go through and explain why for all of them, so definitely fast forward to wherever you need to be. Up first, number one, what is the pH of a 0.25 molar solution of hypochlorous acid, and what is the percent ionization? Now, we can solve this question without knowing what hypochlorous acid is. We can use a placeholder and just say HA for a weak acid, but you shouldn't, if you want full credit, you want to write down what hypochlorous acid is. And you should know what hypochlorous acid is. You guys will learn these. Remember, if we have us acid, that came from ite, which means this came from hypochlorite. You should also know what hypochlorite is because you know your polyatomics. Now, hypochlorite, yes, you should know your polyatomics in general. And if I apologize if you hear a kitten, one of them is right next to me right now and really, really wants attention. So she's yelling at me anytime I stop petting her. Um, Easiest way for me to remember them is remember chlorate, which is ClO3 minus. Therefore, chlorite is ClO minus, and hypochlorite is ClO minus. Remember, ate to ite loses one oxygen but keeps the same charge, and ite to hypochlorite loses a second oxygen, one more from ite, but keeps the same charge. The other thing I want you to remember here is what does it mean to be an acid? An acid takes any anion and gives it enough protons to be neutral. So if I give this one proton, it's now neutral. One proton, it's now neutral. One proton, it's now neutral. So hypochlorous acid is HCl. Oh, it is aqueous because it is an acid, okay? And we're going to put that with water. It does form an equilibrium because, again, weak acids only partially dissociate. It goes with water and it forms the chloride ion and hydronium ion. You should be able to identify anytime something's acting as an acid, a base, a conjugate acid, or conjugate base. So in this case, this is acting as the acid. I know that because it's donating a proton. Remember the donation of the proton, that is the definition of the Bronsted-Lowry acid. Okay? It's donating a proton to the water, so the water is acting as a base. This is my conjugate base, and this is my conjugate acid. So again, the acid goes with the conjugate base, the base to the conjugate acid. Of course, that's not what the question specifically asked us, but it's always good to review those things and understand where those things are coming from so we can actually do the question. What I really want, though, is a 0.25 molar solution. I want to know the pH. Okay? Oops. The eraser's a little too big there. I'm going to erase these things, just get them out of the way so that I can set up the rice chart. How do I know I need a rice chart? Because I have a weak acid. And if I have a weak acid, I'm going to need that rice chart. RICE stands for reaction, initial, change, and equilibrium. I need to know how much dissociating, but I truly don't know because it is a weak acid. So I'm going to have to do a rice chart to figure it out. It's not a strong acid. It doesn't just work. It doesn't just quickly, it's not easy math. I've got 0.25 molar here. Water does not factor into the rice chart because water is a liquid and it's our solvent. Remember, if water was not a solvent, it was a reactant or a product, it'd be a little bit different. But here, water is our solvent, so it doesn't factor into our rice chart. I don't have any of the hypochlorite to start with, and I have approximately no hydronium ion. Again, I say approximate here because I do have some hydronium ion present just due to water, but it's a concentration of 10 to the minus 7th. So relatively small compared to the concentration of the acid here. Change minus x plus x, and equilibrium 0.25 minus x, and x. Now I will need a Ka value here or something here. In the table up here, I need to look up hypochlorous acid. And let's see, I didn't make things easy on us. I gave us hypochlorous acid as a pKa value. So that means I need to undo that pKa value to actually solve the question. I'm going to do that up here. Remember that pKa is the negative log of Ka. So to get to my Ka, it's 10 to the negative pKa. So Ka is equal 10 to the negative 7.52 is equal to 3.0 10 to the minus 8. When I write my K expression here, again, it is Ka because I am producing an acid here. I'm producing hydronium. If I was producing hydroxide, I would do Kb. Because I have hydronium, I know it's Ka. ClO minus concentration times the H3O plus concentration divided by the HClO concentration. Put in what we know, x squared. Again, I am putting in the values from the table itself. I have two x's, it's squared. Divided by 0.25 minus x. And this equals that Ka value I just found, 3.0 times 10 to the minus 8. I just need to solve for x. I am going to follow the 5% rule and check in a minute. Again, the 5% rule usually works if my Ka is small. My Ka is really small. If it's smaller than 10 to the negative 5, it should work. It's 10 to the negative 8. I will check it in a sec, though. So I'm going to assume that my 0 is, basically, I'm going to assume that my x is really small compared to 0.25. Therefore, I can ignore it. That simplifies the math, giving me x squared over 0.25 is equal to 3.0 10 to the negative 8. Solve, mathematically, algebraically, solve for x, and I get an x value of 8.66 times 10 to the negative 5. Now my sig figs are right here. We'll talk about checking the 5% rule in just a sec, because that actually goes along with this question here. When I want pH, remember what pH is. pH is the negative log of the H3O plus concentration. But what did I just solve for? X represents that concentration. So my pH is negative log 8.66 times 10 to the negative 5. This gives me a pH value of 4.06. Now let's talk sig figs. I told you you had two sig figs in this question. That is correct. The 8 and the 6 are what's significant here. On a pH scale, the numbers after the decimal place are your sig figs. This number is due to the log. So this number actually goes based on the log. It's these two numbers down here that are my actual sig figs. So I need two sig figs, two decimal places. I haven't actually checked my 5% rule though, but this goes along with the percent ionization. It's done the exact same way. So percent ionization, you take how much you've dissociated. So again, X is representing how much dissociated, how much broke apart, divided by 0.25. Why 0.25? Because that's what I started with, times 100. This is the exact same way you check the 5% rule too, which is just convenient. When I do the math here, 8.66 times 10 to the negative 5 divided by 0.25 times 100 gives me 0.035%. Definitely less than 5%. So definitely valid assumption. It also shows me that basically hypochlorous acid is a pretty weak acid. Not a lot of it's going to break apart. Only 0.035% is actually dissociating, when I have a 0.25 molar solution. So again, things I had to find here, I had to find my Ka value. I had to set up my rice chart. I had to find my X value to solve my overall pH, and then my percent dissociation. Or ionized. How much actually broke apart. And again, what that means is how much broke apart into H plus ions and ClO minus ions. The next question. What is the pH of a zero point 0.1 molar ammonium chloride solution? Okay, I have to recognize what ammonium chloride is. So first, ammonium chloride. Okay. Number two, what is the pH of a zero point 0.1 molar ammonium chloride solution? First, I need the formula of ammonium chloride. NH4Cl. That's just a salt. So why would it have a pH? I need to recognize that ammonium chloride is a salt and will break apart as a strong electrolyte. So this breaks up into NH4 plus ions and Cl minus ions. One of these will react with water, the other one will not care. And I need to recognize which is which. If I look at chloride, I know chloride comes from HCl, which is a strong acid, which means this is a neutral conjugate base. And what I mean by neutral is it will cause a neutral pH. Chloride won't do anything. Remember, we talked about stability. The reason that strong acids are so stable, are so strong, is because their conjugate bases are very, very stable. Chloride is a very stable base. Chlorine has the extra electron it wants to form the chloride. The size of the ion is good. It can hold on to it really well. It doesn't want to do anything with water. It it doesn't have a proton to give up, so it can't act as an acid. And it's a conjugate base, yes, but bases steal protons back. Chloride doesn't want the base back. It's quite happy having given up that, or doesn't want that proton back. It's quite happy having given up the proton. So this isn't going to do anything. But this guy, this is the conjugate acid of a weak base, which means it will react with water. Because again, if I put ammonia in water, ammonia is NH3. This forms an equilibrium with ammonium and hydroxide. This is my base, my acid, my conjugate acid, and my conjugate base. Conjugate acids of weak bases will react with water because it's an equilibrium reaction, first of all, here. Um, Ammonium will absolutely act as an acid in water, though. So it's going to undergo the following: ammonia, NH4 plus water forms an equilibrium, forming ammonia. Notice it's aqueous, they're not a gas. It's ammonia gas bubbled through water, and H3O plus. So this acts as an acid, a base, the conjugate base, and the conjugate acid. First, I have to recognize the ammonium chloride will even do that. So you have to be able to recognize the salts, what they'll break up into, and what the species will do. But I've got an acid here, so I expect the pH to be less than 7. Did I write that the right way? Get that out of the way so we can write there. Okay. So I know the pH should be lower than 7. How much lower? I don't know. I'm gonna find that out. Let's go check what I have for ammonium up here. I don't have anything about ammonium, but I do have the Kb value listed for ammonia, 1.8 times 10 negative 5. So I'm gonna have to use that Kb value to find the Ka value over here. Might as well do that now. I know that Ka times Kb equals Kw. I know at 25 degrees Celsius, which unless otherwise stated, I'm going to assume 25 degrees C, that Kw is equal to 1.00 10 to the negative 14. I need Ka. I know Kb is 1.8 10 to the negative 5. This gives me 5.6 10 to the negative 10. So I know my Ka value. Cool. I'm going to move that up here. And I'm going to get rid of this because I'm going to need space. Need to rewrite my reaction down here so I can write my rice chart. NH4 plus, H2O, NH3 aqueous, NH3O plus. So again, my ammonium is acting as an acid, water is acting as a base, ammonia is the conjugate base of ammonium, and the hydronium is the conjugate acid of water. Told I have a 0.1 molar solution here. Water doesn't factor into it because it's a solvent. I don't have any of this to start, and I have approximately no hydronium to start. Again, approximately because we are assuming that the contribution from water is negligible comparative to the amount coming from the ammonium chloride. Minus x plus x plus x, 0.10 minus x, and x. I am setting up a Ka expression again because I got the K expression, but I've got hydronium in the in my product side. So that's going to go in my numerator. So I'm going to write Ka because I'm looking at how much acid dissociated formed acids form hydronium ions. It's the Arrhenius definition. It's the most basic definition we have. Times the hydronium concentration, oh, say ammonia concentration times hydronium concentration divided by the ammonium concentration. Plug in what we have from our table. X squared, 0.10 minus x equals 5.6, 10 to the negative 10. Most likely the x can be ignored because 5.6 times 10 to the negative 10 is very, very small, but we will check our assumption in a minute. Let's go ahead and solve this out. Let's see what is the actual numerical answer for x. X is equal to 7.45, sig figs are here, times 10 to the minus 6. Two sig figs because I started with 1.8 for the Ka value from the table, therefore I have two sig figs here. But remember what x represents. X represents the hydronium concentration in my equilibrium. pH equals the negative log of H3O plus concentration. So the negative log, 7.45, 10 to the minus 6. And I get a pH here of 5.13. So it is less than 7 as predicted, but it's not, a little bit higher than the one over here. Why? Well, it's the conjugate acid of a weak base. It's not going to be as strong of an acid. It's an acid, yes, but it's still the conjugate acid of coming from a weak base in the first place. But we should probably check our assumptions. So let's go ahead and do that. To check the assumption, you just do the same thing we did for percent ionization. I'm going to take the amount that's associated, which is this, divide it by the amount I started with, the amount, or rather, the amount I ignored it from. Excuse me, the amount I ignored it from, and multiply by 100. So check assumption. I have 7.45, 10 to the minus 6, divided by 0.10 times 100. This gives me 0.0075%. So assumption's valid. So what I did right here, completely valid. Also, as a reminder, I had two sig figs in my answer, and that all limited by the Ka in the first place. And so that's why I have my pH listed as two decimal places, because decimal places are where you have your sig figs. The 5 in front is due to the log itself. Okay, let's look at number 3. What is the pH of a point? Number 3, what is the pH of a 0.25 molar solution of ammonia? You guys just need to know what ammonia is. So ammonia, again, NH3. It's aqueous, it's dissolved in water. It's NH3 gas, just boiled through water. And it reacts with water in an equilibrium to form ammonium and hydroxide. So you guys need to know ammonia's formula and that it is a base. This is your base. So in this case, water is an acid. This is our conjugate acid. And this is our conjugate base. Again, bases accept protons. Okay. We also say it as they're being protonated. So again, accept proton is protonated. Donate proton, deprotonated. So deprotonated meaning it got rid of a proton. Protonated meaning accepted a proton. So I will try to use the words protonated, deprotonated just to help you guys get ready for organic, but I will more naturally use donate and um, accepted a proton. Ammonia, the conjugate base again, or ammonia is the base, conjugate acid is ammonium. In this case, water is acting as an acid, and its conjugate base is hydroxide. We know from the previous question that our Kb value is 1.8 times 10 negative 5 for ammonia. So that part's nice. I don't have to do any calculations. I just need to use it straight out. Sometimes that scribbling works so well, and then there's the rest of the times in my life. Okay, let's set up your rice chart. Initially, I have a 0.25 molar solution of ammonia. And again, your rice charts are molarity. You can, if you're doing straight gas equilibrium, you can also use pressure in your rice charts, but for acid base chapter, they are molarity. Water doesn't factor in. I don't have any ammonium to start here because there's none mentioned. And my hydroxide concentration is approximately 0. Again, approximately because water itself has a hydronium concentration of 10 to the negative 7 under just natural pH 7 conditions. But we're assuming that the dissociation from the ammonia here will be a lot stronger. Minus x plus x, because some of the ammonia will accept a proton from that water, forming ammonium and hydroxide. We just don't know how much yet, hence the placeholders of x. At equilibrium, I have 0.25 minus x, and x. When I set up my k expression this time, it's going to be a kb. And that's because I've got ammonium here, but I've also got hydroxide. So again, if I've got hydronium in my numerator, in my K expression, it's a Ka. If I've got hydroxide, it's a Kb, B for base. And then I got ammonia here. Plug in what we know from our table. Again, x and x, and 0.25 minus x. So I've got x squared over 0.25 minus x, and this equals that 1.8 times 10 negative 5 that we'd written down for ammonia already. Go ahead and solve for x. Excuse me. And x here is equal to 0.00212, but I do need two sig figs, so technically it's 0.0021. I'm just carrying one extra digit right now to prevent round off error. And remember what this means. This is equal to my hydronium concentration at equilibrium because it represents X, which is my hydronium concentration. So when I take the negative log of that, I'm actually going to find POH. I have a few different ways I can do this. I can convert hydroxide to POH to pH, or I can convert hydroxide concentration to hydronium concentration to pH. I prefer to go through POH because I prefer to get the log out of the way right away. Negative log 0.00212 gives me a value of 2.67. But I have to recognize I'm not done. Few key things. First of all, this is a base. Bases need to have pHs above 7. This one is definitely below 7. Two, I just calculated POH. I am being asked for pH. So I need to recognize what I'm calculating and that I am not done. Remember that pH plus POH equals 14.00. Therefore, pH is equal to 14.00 minus 2.67, which is 11.33. My actual pH here is 11.33, which matches. That makes sense for a base. I also need to check my assumptions here. I'm going to do that up here. I'm going to look at how much actually dissociated, which is the value of x here, and compare it to what I ignored it from, for lack of better English there. And then multiply by 100%. So 0.00212 divided by 0.25 times 100%, 0.85%. My assumption is valid, and I am safe in how I calculated my pH. Again, the question only asked for the pH, didn't ask me to check my assumption, but the chances of you checking your being told to check your assumptions on assessments is pretty high. So I'm trying to show you guys how to do it now, so that you know what you do when you get those questions. What about the pH of a 0.3 molar sodium fluoride solution? I need to recognize what sodium fluoride is. It is a salt. It splits up into sodium ions and fluoride ions. When a sodium ion is in water, is it going to do anything? It doesn't have any protons to donate. It doesn't want to steal one from water. Sodium is quite happy. Doesn't want anything. It's a sodium ion. It's just going to float around in solution and nothing's going to happen. What about the fluoride? When I put fluoride in water, it does do something. The fluoride ions will accept a proton or protonate, forming HF and leaving behind hydroxide. So it accepted a proton, it was protonated, it is a base, water's acting as an acid, this is the conjugate acid, and the conjugate base. So again, you need to be able to look at these things and recognize what's actually happening here. Let's set up your rice chart. I should not be trying to circle things when I'm tired and not paying attention. We're going to pretend that's good enough. Okay, so the fluoride concentration here is 0.30 molar. And I forgot to mention that on the ammonium chloride concentration above. But remember, if I have a 0.3 molar sodium fluoride, that means I have 0.3 molar sodium ions and 0.3 molar fluoride ions. So it stays the same value. If I had something dissociated of two things, well, then I'd have to pay a little more attention. So if I had like, excuse me, magnesium fluoride, I'd have to pay attention. But in this case, it's a 1-to-1 ratio. Water, no HF to start, and approximately 0 hydroxide. Minus x plus x plus x, 0.30 minus x, and x. I have no idea what the actual value is for fluoride, so let's scroll up. Okay, we've got a hydrofluoric acid here. That's helpful. HF value of 8.9 times 10 to the negative 8. The Ka here, 8.9, 10 to the negative 8. But looking at this question, is this the Ka I need to write? Or do I need something else? My K expression here for the equation as written is HF times OH minus over F minus. I've got that hydroxide right there, which means I really need Kb. So although I know what Ka is, I need my Kb. Remember Ka times Kb equals Kw. Kw is 1.00 times negative 14 at 25 degrees C. My Ka was 8.9 times 10 to the minus 8. And hold on, because I don't actually know off the top of my head. Ammonia is the only one I know off the top of my head. Let's see, 1.39. Sig figs are here. Times 10 to the negative 11. So this is equal to 1.39 times to the negative 11. And if I plug in what I have in my table, I have x squared over 0.30 minus x. I'm going to solve that question for x. I get an x value of 2.04 10 to the minus 6. But again, remember what x represents. X represents the hydroxide concentration at equilibrium. So again, you can go through, I don't care which way you do it. I'm going to erase this stuff over here for space. You can use the equation H3O plus times OH minus was 1.00 times 10 negative 14. You can plug this into here and solve for this and find pH, or you can use pH plus POH is equal to 14.00, which is what I do because I find it to be easier. My POH is equal to the negative log 2.04, but my sig figs are here, times 10 to the minus 6, which gives me a pOH value of 5.69. Now I'm running out of room. So pH 14.00 minus 5.69 is equal to 8.31. So the pH of this system, 8.31. Of course, we do need to check our assumption, because we did make an assumption here that this went to 0, and that's how I simplified and solved the math a lot faster. My assumption, okay, I truly don't know where it stopped talking because the app froze again. So hopefully you guys heard me, but I said, I had made the assumption that the x down here was very negligible compared to 2.3, so I ignored it to simplify the math up here, but I need to check that assumption. To do that, I take x divided by the initial value times 100%. In this case, my x value is 2.04 times the minus 6 divided by 0.3 times 100%, and I get a value of 6.8 times 10 to the minus 4%. My assumption is valid, so it was completely valid in assuming that x was very, very small compared to 0.3 to solve the overall question.
Number 5. The pH of a 0.200 molar weak monoprotic acid is found to be 3.50. What is the Ka of the acid? Here, I don't care what the acid is. It doesn't matter, okay? And that's part of the reason I'm using this example is that the identity of the acid isn't what's important. The fact that I know how many protons it has, how many ionizable protons it has is what's important. Monoprotic means I can lose one proton. So I'm going to call it HA for simplicity, okay? If I have HA, and I know that the pH of the solution is 3.50, remember what pH means? pH is the negative log of the H3O plus concentration, which means that that value equals 3.50. But that means I can undo that to find the concentration of HA. Therefore, my concentration of H3O plus is equal to 10 raised to the 3.50, which is the same as 3.16 10 to the negative 4 molar. Now, let's talk about sig figs really quickly. Remember, when you're in the log form, it's the decimal places that are significant. So this actually only has 2 sig figs and it stops here. I'm just not going to round yet. I don't want to round yet. But my actual hydronium concentration in this system is 3.16 or 3.2 times 10 to the negative 4 molar. But that gives me an idea of how to solve the question for Ka, because what that is the equilibrium concentration of hydronium. If I set up a K, or if I set up an equilibrium, if I set up your rice chart, I'll get it eventually. HA plus water, I know forms an equilibrium, and I know this forms my conjugate base, A minus, and H3O plus. I know that, I don't know, let's see, what do I know? I know this, I know I had a 0.2 molar solution to start. Water doesn't factor in. Minus X and 0.200 minus X. I know I had no conjugate base to start, and I know that I have approximately no H3O plus, because really, again, what I have is 10 to the minus 7 molar here, which is probably small enough it's insignificant. Plus X, X and X, okay? I know that, but I also know, based on my pH, that I can, sorry, I'm trying to keep a cat off. I know this correlates to here, and is the value of X here. So I actually do know the equilibrium concentrations of each species. If I do that math, that gives me 0.200 molar still for the HA concentration, because the 3.16 times 10 to the negative 4 is statistically insignificant when I do that subtraction. Again, that's like saying 0.200 minus 0.12. I forgot a zero there. There you go. That. When I subtract those out, based on sig figs, I'm still going to get this value. This value here, 3.16 times 10 to the negative 4 molar. And this value here, 3.16, 10 to the minus 4 molar. I'm going to go ahead and shrink everything we've written so that we can write out our K expression here. It is a Ka expression because it is an acid dissociation. Again, if I ever got confused on that, I know I've got hydronium written into my K expression, which means definitely an acid. I know my equilibrium concentrations. I've got 3.16 times 10 to the negative 4 for my A minus, or my conjugate base concentration equilibrium. I've got 3.16 times 10 to the minus 4 for my hydronium concentration equilibrium. And I've got 0.200 for my concentration of my weak acid equilibrium. Calculate that out. I get a Ka value, 5.0 times 10 to the negative 7. Remember, sig figs here, this was limited to 2 sig figs. I forgot to draw it underneath there again. But it is 2 sig figs based on that pH originally, so my final answer can only have 2 sig figs, stopping here at 5.0. So I know the Ka of this acid is 5.0 times 10 to the negative 7. I can use that information to figure out what the heck the identity is of that acid. Arrange in order of increasing acidity from left to right. Potassium cyanide, hydrocyanic acid, rubidium hydroxide, methyl ammonium chloride, lithium nitrate, and perchloric acid. Okay. First thing I want to do is figure out what the formulas are and if they're acidic, basic, or salts from the start. Potassium cyanide, I know potassium is K, cyanide is Cn. That is definitely a salt. So it could be acidic, basic, or neutral. I'll come back to that one. Hydrocyanic acid is a weak acid. I know it's an acid because it says acid. I know it's weak because it's not one of the ones I have memorized as strong. And HCN is its formula. Rubidium hydroxide, RB, and then I never actually remember if rubidium is group 1 or group 2, so I just looked it up on the table really quick, which of course I do not have in front of me. So let's see, rubidium is group 1, so it is just 1 hydroxide for every rubidium. And that is it is one of the strong bases. I know that. I just never remember where it is in the table. Let's see, rubidium. Next I have methyl ammonium chloride. I've got the ammonium thing going on here and a chloride. That's definitely telling me a salt. Okay. And it's giving you the formula right here. I've got lithium nitrate, LiNO3. That is also a salt. And perchloric acid. Remember, ic acid comes from 8. So perchlorate is ClO4 minus. This is HClO4. And this is one of my strong acids. So I want this in order of increasing acidity, okay? I know that anything that's an acid is going to be the strongest acidic, and that's basically be the weakest acidic, and then my salts are going to fall somewhere in between. Where? I don't know yet. My salts and my weak acids and weak bases will fall somewhere in between. I just don't know where yet. But I can quickly say that rubidium hydroxide will be my least acidic, and HClO4, or perchloric acid, will be my strongest acidity. Why? Because I just said I'm ranking them in order of increasing acidity. Excuse me. And HCl is a strong acid, so it's the only strong acid in the list. It's got to be the strongest. And rubidium hydroxide is a strong base, so it's going to be the weakest. So for ease, I'm going to erase a little bit of what I wrote so that we can stop focusing on those ones. And I'm going to cross them out. Try to simplify this list for my brain. Okay, now I've got KCN, HCN, lithium nitrate and CH3NH3Cl. Okay, hold on. I'm making sure I'm not missing something. Okay, sorry. In my notes, so if you're using the notes format for this, I've wrote hydrosulfuric acid, which is H2S here, with hydrocyanic acid. It's going to work the same. They're going to be in the same order. But if you're getting confused between the notes I provided and the video, it's because I just wrote the wrong compound in here, but it's going to work the same. I'm going to have to look at their Ka values of these things and then see how they're behaving. And so first, let's look up hydrocyanic acid. I think I gave you the value for that one. Let's hope I did. If not, I'm going to have to look that up quick. I did not give you hydrocyanic acid because it is the wrong compound listed here. I didn't mean to write that one on this slide. So let me look that up really quick because I actually don't know that value. Okay, the Ka for hydrocyanic acid is more difficult to find than I expected with a quick Google search. Okay, 4.9, 10 to the minus 10. Okay, that's its Ka value. Let's think about these other things. KSCN, methyl ammonium chloride, and lithium nitrate. Okay, I have to think about the fact of what are these salts going to do in solution. If I have let's do lithium nitrate first. It's the easiest one. If I have lithium nitrate in solution, this splits up into lithium ions and nitrate ions in solution. This compound will have a pH that is neutral. Why will it do neutral? Because the cations want to react and form hydroxide, come from hydroxide species. So what I mean by that is, so I gave this a hydroxide species. Lithium hydroxide is a strong base. Lithium doesn't want to take a proton. Okay, first of all, it doesn't want anything to do with taking a proton. That's the first thing bases will do. They'll take a proton. So if it can't take a proton, it's already positively charged. It's not going to take a proton. Then I think about the fact that if I had given it hydroxide, what would it come from? It came from a strong base, which means that its conjugate acid, in this case lithium plus, is a neutral species. The nitrate, if I gave that a proton, it is negative charge. Protons are positive charged. So I gave that a proton, I'd have HNO3, nitric acid, which is a strong acid. That isn't going to do it. It's not going to do anything. This species is going to be neutral. Basically, neither lithium nor nitrate want to pick up or donate. Neither one has a proton they could donate, and neither one wants a proton. They're both super stable in solution, so neither one's going to pick up a proton, and nothing can donate a proton. So that makes that salt neutral. It is a salt, but it makes it a neutral species. I have to figure out on the other sides if they'll be acidic or basic. If I look at potassium cyanide, this breaks up into K plus and Cn minus. Again, neither species has any protons they can donate, okay? So if I look at K plus, it can't accept a proton. It's already positively charged. And this comes from KOH, which is a strong base. So the K plus isn't going to do anything to solution. But the cyanide here is absolutely willing to accept a proton, forming HCN, hydrocyanic acid. What that means is that this species that's left behind, this is the conjugate base. It will react with water. It will pull a proton from water. Forming HCN and hydroxide. So this is a basic salt. I'm trying to fit it in here and it's not working very well. And it's basic because of that cyanide compound. Cyanide ion there, okay? So get that out of the way. I already know that this is acidic. Okay, I know it's neutral. Okay, methyl ammonium chloride. If I put this in solution, CH3NH3 plus and Cl minus. The chloride comes from HCl, which is a strong acid, which means that chloride is not going to pull a proton back. It wants nothing to do with that proton. It would like you to leave it alone. So that is going to be a spectator, not doing anything to solution, kind of like the potassium above. But this species is the conjugate acid of a weak base, meaning it can donate a proton. CH3NH3 plus water can form CH3NH2 plus H3O plus. So it's acting as an acid because it's donating that proton. Because it's able to donate that proton, it's acting as an acid, and it's going to be acidic species in solution. So let me erase this out of my way. Okay. So I know this is acidic. Okay. I know that the KCN is basic. So that crosses that out. I know that the lithium nitrate is neutral. Okay. That crosses that out. Now all I have left is the hydrocyanic acid and the methylammonium chloride. And so I need to figure out which one is more acidic. And I do that by looking at that chart. Here I've got methylamine listed. I'll talk about this in a sec. My methylamine here has a Kb value of 4.4 times 10 negative 4. Okay, so if I go back to that slide, my methylamine which is CH3NH2 is methylamine, has Kb, I already forgot. Doing great. 4.4 10 negative 4. I have the Ka of the other one. I just need to compare them. I need to get them to the same unit, though, and I don't have this written down. So let me get out a calculator. See if I can find one that works in front of me. Okay. Remember, Ka times Kb equals Kw. I don't care which one you convert them to. I'm going to convert both to Ka. So I'm going to find the Ka here. So 1.00 10 to the minus 14 divided by 4.4 10 to the minus 4. Gives me a value of 2.3 10 to the negative 11 for the Ka here. But again, that is a measure of how likely that methylammonium is to give up that proton. And I see that its value is slightly smaller than hydrocyanic. Hydrocyanic acid doesn't have a large Ka value. It's very small. 4.9 times 10 to negative 10 is small. But it's still larger than 2.3 times 10 to negative 11. Therefore, it's still the stronger acid. So I will have this CH3 and H3Cl here, and the HCN here in order of increasing acidity. So I've had to think about the fact that what are strong and what are weaks. Figure out my strongs right away. My strong acids and bases will be the extremes. Figure out what's neutral. That's going to go in the middle. It's not going to test pH. It's not going to change your pH at all. Then from there, I only had one weak base, which was this one. I only had one weak base. So weak base. And then I just had to compare my acids. So again, weak base, weak acid, strong base, weak acid, neutral, and strong acid. And my weak acids, I just compared their Ka values. The bigger the Ka, the stronger the acid. Using the following Ka values indicate the correct order of base strength. Okay, so this is where you need to remember the connection between acids and bases. Remember, the stronger the acid, the weaker the base. Why? Let's use HCl as an example because chloride's in here anyway. HCl is a strong acid because in water, it completely breaks apart, donating all of its protons to make hydronium ions and leaving chloride behind. It's able to do this because of the stability of this, the conjugate base. The more stable, so remember, it's because they have a more stable conjugate base. Stability does not equal strength. Stability is it doesn't need the proton. It doesn't want it back. It's very, very stable the way it is. So stability and strength are not the same thing. Strength is how willing is it to act as a proton or donator, proton donor or acceptor. How likely is it to act as an acid or a base, okay? The strength comes from the stability of the conjugate. So strong acids have weak bases, but very stable bases, conjugate base specifically. Also remember, the larger the Ka value is a stronger acid. So let's look at the species we have down here. We have HNO2, which is nitrous acid. We have HF, which is hydrofluoric acid, and HCN, which is hydrocyanic acid. And I also can see I have some water and some chloride in here, okay? So chloride, well, I just erased, but chloride comes the conjugate base of HCl. This is a strong acid, which means this is a stable base, which also makes it a weak base. Okay? I have water. Water is amphoteric or amphiprotic. Meaning it acts as an acid and a base. And it will be neutral in how it's going to act. The NO2 minus is the base form here. The F is the base form here. And the CN minus is the base form here. And that's why you see what you see below. These all come from weak acids. So all of these are weak acids, which means that the nitrite, the fluoride, and the cyanide are all weak bases. I'm going to compare the Ka values, and the smaller the Ka, the stronger the conjugate base. Notice below the way these arrows are listed is by strength. So I want them indicate the correct order of base strength. The way the little triangle alligator here is telling me this is bigger to the left and smaller to the right, which means that I want whatever I pick here needs to be basic over here and less basic or weaker base over here. So stronger base, weaker base. Okay? Right away, I know, without even thinking about it, that cuts this one out. Because B is telling me that chloride is my strongest base. I know for a fact chloride will not be a strong base. Chloride is the conjugate base of a strong acid, which makes it weaker than any of these people. These ions. Any of these ions. It makes it weaker than any of these because they all come from weak acids, which means they will all be stronger as a base than chloride. Because chloride is super, super stable. It's not going to pick that proton back up. All of these, nitrite, fluoride, and cyanide, are likely to pick up that proton again. For the chloride versus the water, I'll talk about that one in a minute. Let's go ahead and look at the other species we have. Okay, or the other information we have. We have the Ka values, and that's actually a lot of information. The Ka values listed here tell us a lot. Remember, the larger the Ka, the stronger the acid, okay? That means that this list, this is the weakest acid of the list of these three, I mean. And then 4.0, 10 - 4, and 7.2, 10 - 4, this is the strongest acid of this list because 7.2 is greater than 4.0, and they're both 10 - 4. But that means on the flip side of it, on the basic side of it, that this is the strongest base of this list because it has the least stable conjugate base. This is the weakest base of this list because its conjugate base is the most stable of these three. And then the HNO2 acid or the nitrite for the conjugate base is in between those two. But that means that my cyanide, I just figured out, is my strongest base. So I can cross off D. Now, before I talk about the water and the chloride, I can even figure out the answer here. Looking between these two, I know that the HF is stronger of the two of these, which means this is the stronger base of the two of these. The nitrite specifically is stronger base than the fluoride. So I know right now that my answer needs to be A. I've got the cyanide, then the nitrite, then the fluoride, then the water, and then the chloride. But why water, then chloride? Again, water's neutral. It's going to form, we know it undergoes autoionization, acts as an acid or a base, but it's coming from a neutral perspective. Chloride is coming from such a strong acid that it's never picking that proton back up. It doesn't want it. Water will do it, 1 in 10,000. So the water is still a stronger base than the chloride because chloride came from such a strong acid that its conjugate base is so stable that it's not going to do anything. It's not going to pick that proton back up. Number 8, sodium benzoate is a common food preservative. What is the pH of a 0.25 molar solution of sodium benzoate? Now, I don't expect you to know the formula of sodium benzoate on an exam, okay? If I don't give you the formula, and that's what I purposely do in this one is I don't give you the formula, and you don't know what it is, if it's something that you should know, you know your polyatomics, therefore you know how to make their acids, all of that. Yes, you have to do that. But something like sodium benzoate, you haven't learned it, that's fine. You need to recognize, though, if this is acidic or basic. You need to recognize what this is coming from. When I see that word sodium here and not hydroxide after it, it's not a base. This is a salt. Sodium benzoate is so sodium benzoate splits up into sodium ions and benzoate ions. And benzoate is a conjugate base of a weak acid. That update was serious, driving me nuts on this thing. Specifically, it's the conjugate base of benzoic acid. And again, how would I know that if I don't know what benzoate is or benzoic acid is? Well, because I know that it says sodium in front, and sodium means it's going to be a salt if it's not a hydroxide. It's just that simple. Because it's a base, I'm going to need Kb. I look at the list I gave us, and the list I gave us has, let's see, benzoic acid listed right here, and it's giving me a pKa value of 4.19. So I'm going to use that information to find the Kb. It gave me pKa equal to 4.19. That means I can find the Ka. Remember, Ka is 10 to the negative 4.19. So 6.46, 10 to the negative 5. Let's talk about sig figs really quick. This had 2 sig figs because it's in the log form. It's the numbers after the decimal place, which means that my sig figs are right here. I'm going to carry that extra digit right now, but I need to recognize I only have 2 sig figs. And I do need KB, not KA. So we're KA times KB is equal to KW, which is equal to 1.00 10 to the negative 14. So my KB is 1.00 10 to the negative 14 divided by 6.46 sig figs times 10 to the negative 5 gives me a 1.55 times 10 to the negative 10. And I'm just going to underline my sig figs right there. So I've got my KB. Great. Now I can actually set up my expression. So I am told I want to know the pH of the solution. Okay. I don't actually know what the formula is, though, of benzoate. What am I going to do? I know it's the conjugate base of a weak acid. So I'm going to use A minus as a placeholder. A minus means conjugate base of a weak acid. Put that in water. Form HA, which is my weak acid, in this case benzoic acid, plus hydroxide. It is acting as a base, so it's forming hydroxide, plus it pulled the proton off water. What's left is hydroxide. Set up your rice chart. You start off with a 0.25 molar solution. Water doesn't factor in. We have no HA to start, and we have approximately no hydroxide. Again, approximately, because really we have 10 to the minus 7 molar present just from water. Plus X, X, and X. When I set up my K expression here, I'm actually setting up KB. Again, I know it's B because the species is acting as a base, but also if I ever get confused, I know I've formed hydroxide, and because hydroxide is in my K expression, I better be using a KB. This gives me X squared over 2.5 minus X based on my equilibrium expression here. So I just plug these values in to here. And this is equal to 1.55 10 to the negative 10. Definitely don't have room, so let's make some. Okay, I'm just going to leave that like that. Okay, for simplicity, we're going to follow the 5% rule. We're going to assume this x is so small I can ignore it, which simplifies the math, giving me x squared over 0.25 equal to 1.55. Again, my sig figs are here, times 10 to the negative 10. When I solve for x here, so algebraically solve for x, 1.55 times 10 to the negative 10 multiplied by 0.25, take the square root of that, and I get a 6.22 10 to the minus 6. I'm still checking my sig figs. I still have 2 sig figs. But remember what this equals. X is equal to the hydroxide concentration at equilibrium. So this is equal to hydroxide. So for ease, I'm going to find the pOH first, and then I'll find pH. Negative log 6.22, underline my sig figs, times 10 to the minus 6. Gives me 5.21. Remember, when you go into the log form, it's the numbers after the decimal place here that are your sig figs. So 5.21 has 2 sig figs to it. But I really need pH. pH plus pOH equals 14.00. So if I solve this, my pH has to be equal 8.79. I then ask myself, does my answer make sense? And I say, well, I've got sodium benzoate, which I know is a base, and my pH is above 7. Yes, my answer makes logical sense. If you had to check your 5% rule, remember the 5% rule is you take the value of x, so you take the value you've ignored, okay, the value of x, and you divide it by the value you've ignored it from. So 6.22, 10 to the minus 6th, divided by 0.25, and multiply that by 100 and see what that 100%, and let's see what that value is. 6.22 e to the negative 6 divided by 0.25 times 100 gives me 0.025%. Yeah, that's less than 5%. And it's probably a pretty good guess that it would be because our Ka value was so incredibly small. So again, pH of this one, 8.79. Okay, which of the following is a basic salt? Well, let's think about what's in these things. Sodium chloride. Okay, which of the following is a basic salt? Let's think about the formula of each one of these. Sodium chloride, NaCl. What does this split up into? Na plus ions and Cl minus ions. Neither have a proton they can give up, so they can't act as an acid that way. Neither one have a nitrogen to take a proton away. Neither one are going to be willing to donate their lone pair of electrons to gain a proton. If you think about it from the hydroxide and or from the acid-base perspective, Na plus came from NaOH, which is a strong base, so its conjugate acid is going to be neutral. Cl minus chloride came from HCl, which is strong acid, so its conjugate base, which is chloride, is going to be neutral. So this is going to be a neutral salt. Not acidic, not basic, just neutral. What about ammonium chloride? This comes from NH4 plus and Cl minus. That NH4 plus, the Cl minus is what we just talked about, right? I know chloride is the conjugate base of a strong acid. It's not going to do anything. But this is the conjugate acid of a weak base. So it's going to be acidic. It's going to donate a proton, but it's not going to be basic. What about potassium nitrite? K plus and NH2 minus. The K plus is kind of the same idea as the sodium hydroxide above. It can't donate anything. It's not going to gain a proton because they both have a positive charge. And it came from KOH, which is a strong base, meaning it is going to be neutral in solution. But the nitrite can absolutely take a proton from water. This is the conjugate base of a weak acid. It came from HNO2. HNO2 is a weak acid, which means that this NO2 minus conjugate base will cause the solution to be basic. Because that nitrite in solution will happily take a proton from water to form some HNO2 back. So let's look at the options. Okay, definitely need to reformat this slide. I apologize. So these should not be here. This should be A, B, and C. What are the options? I know they're not all basic or all acidic. I know that they're not all, well, none of these options are correct. I need to fix the slide. Not all basic. I know that the only one, neither A, B, nor C are basic. That is incorrect as well. The only one that is actually going to be basic is potassium nitrite. Because again, that nitrite is the conjugate base of a weak acid, which means it itself will act as a base, and it will grab a proton. It will grab a proton from water. So this will be a basic salt. Is the solution with hydroxide concentration 9.8 times 10 negative 11 molar? Is that acidic, basic, or neutral? What do you guys think? If I look at that pH level, I mean, I could calculate it, right? I could do it conceptually or I can calculate it. So let's think about it. If I am neutral, my hydronium concentration equals my hydroxide concentration, and they both equal 1.0 times 10 negative 7 molar. That's neutral. It's definitely smaller. Than that. So I have less hydroxide than I do under neutral conditions. These are a teeter-totter. If one increases, the other one decreases. If one decreases, the other one increases. So if this concentration here is smaller than that, that means this has been increased, this has been decreased, which means it's acidic. We can also just calculate it though. POH, negative log 9.8 times 10 negative 11 gives me a pOH value of 10.01. pH 14.00 minus pOH 3.99, and it's showing acidic. What is the hydronium concentration of a solution with a pOH of 8.7? So I know if pOH is 8.7, that's the same as the negative log of OH minus concentration, okay? So to actually find the OH minus concentration, 10 to the negative pOH is 10 to the negative 8.7, 1.9 times 10 to the negative 9. Molar is the hydroxide concentration. I know that hydronium concentration times hydroxide concentration equals 1.00 10 to the negative 14. So I can just solve for that. Therefore, I know my H3O plus concentration, 1.00 10 to the negative 14. Divided by 1.9, 10 to the negative 9 is 5. Let me check this because I need to make sure I got my sig figs. 1 e to the negative 14 divided by 1.9 e to the negative 9. 5.3 times 10 to the negative 6. And that's my hydronium concentration. Now, that's one way of solving it. I do have another way of solving it. I'm going to show you really quick. So pause the video if you need to write that down. But I know some people don't really like doing it that way as much. So the other way you can do it is that we know that pH plus pOH equals 14. So therefore, pH must be 14 minus 8.7. Which gives me a 5.3. And I know my hydronium concentration is 10 to the negative 5.3, which is 5.3 10 to the minus 6. That's where my sig figs were, what they were. That's right. I need to pay attention. I apologize before. It should have been 5. 5 times 10 to the negative 6 is my actual answer here, even what I wrote previously, because there's one sig fig here, which means one sig fig here. So 5 times 10 to the negative 6. Number 12, what is the hydronium concentration of a solution with a pH of 0.824? Well, same thing. H3O plus concentration is equal to 10 to the negative pH. So 10 to the negative 0.824. My H3O plus concentration, 0.150 molar. What about number 13? What is the pH of a 0.1 molar perchloric acid solution? I need to recognize that perchloric acid is a strong acid. As such, it dissociates 100% in solution. So HClO4 aqueous breaks into H plus ions and ClO4 minus ions. But if I started with a 0.1 molar solution here, that means I have 0.10 molar here and 0.10 molar here. I want pH, so that's dependent upon the hydronium concentration. pH is the negative log of H plus concentration, so negative log of 0.1. I had 2 sig figs in my original number, so I need 2 decimal places. My pH will be equal to 1.00. Number 14, what is the pH of a 0.0010 molar sodium hydroxide solution? Let's see. Try not to have to pull the calculator back out. And I don't know all the answers by heart. I know how to do it. I just don't know the numerical numbers by heart. Okay, let's see. Sodium hydroxide we know is NaOH. We know this is one of our strong bases. We know it dissociates 100% in solution. NaOH. Don't write plus water when you're dissociating a strong base. It's happening in water, and we're emphasizing that we're writing the AQ. If you have a weak base, make sure to write that plus water because you have to show where that proton is coming from. Let's see, I have 0.0010 molar NaOH, which means I really have 0.001 molar Na plus ions, which are spectators, and 0.0010 molar hydroxide ions, which are not spectators. This is what I care about. So again, you can calculate one of two ways. I'm going to go through POH because I just find it to be faster for me. Negative log of hydroxide concentration. So negative log 0.0010 is 3. 2 decimal place, or 2 sig figs, so 2 decimal places. And then pH would just be equal to 14.00 minus POH, or 11.00. You don't have to do it that way. You can also remember H3O plus concentration times hydroxide concentration equals 1.00 10 to the negative 14. So you can plug your concentration in here and then solve for this value and then plug it into pH if you would like to do that instead. What is the pH of a 0.1 molar hydrochloric acid solution? Hydrochloric acid, HCl is our strong acid. So I know it's going to dissociate 100%. HCl breaks up into H plus ions and Cl minus ions. If I had 1 molar HCl, that means I have 1 molar H plus and 1 molar chloride. But again, the chloride is a spectator. I only care about the H plus here. So my pH is equal to the negative log of 1.0. And negative log of 0, or the log of 1 is 0, so the negative log of 0 is still 0. My pH is 0.00. 2 sig figs, so put those 2 zeros there. Okay, I need to emphasize that I am precise this 0 position here. I purposely put this example in because students get really creeped out by pH being lower than 1. Again, that pH scale of 1 to 14 is just because it's based on water, and it's based on that Kw value at 25 degrees C. Okay, so yes, the pH can go above or below. It can go below 1. It can go above 14. Number 16. Write the reaction of each species below with water and identify the conjugate of each species. Okay, so hydrocyanic acid, that is HCN. So I'm going to write the formula down here. I'll write the thing up on top, but then pause it to write down, so we're going to erase it. HCN, when I put this into water, this is a weak acid. It tells me acid, and it's not one of the ones I have memorized, so I know it's got to be a weak one. But that also means I get those double-headed arrows, okay, those equilibrium arrows. This forms H3O plus and Cn minus. This is acting as an acid, which means this has to be acting as a base. Water is amphiprotic, meaning it can act as an acid or a base. So it's going to do opposite of whatever the other species did, okay? This is an acid, and it formed what's left over after the reaction. It's going to annoy me now. 1 second. Is called the conjugate base. The water formed the conjugate acid. So HCN is the acidic form, Cn minus is the conjugate base. In this reaction, the H2O was the base, the H0 plus is your conjugate acid. Acetic acid, CH3COOH, also a weak acid. So CH3COOH plus water, equilibrium arrows. It is an acid, so it's going to donate that proton. And H3O plus. This is an acid, so this is my conjugate base. This is my conjugate base. Wrote it in the wrong spot this time. Or a different spot, not the wrong spot. It's my conjugate base, which means this is behaving as my base. And this is my conjugate acid. Again, water can act as an acid or a base. Okay, what about ammonia? You need to know ammonia. You just do. Like, there's no exceptions to that. You need to know the formula for ammonia is NH3. Ammonia, when put into water, really wants to act as a base. It's when it's happiest. It has a lone pair on that nitrogen, and it wants to accept a proton to it. How many? Yeah, not a ton. Depends on the concentration and the temperature, but it does want to accept some protons. In doing so, it forms ammonium and hydroxide. So this is acting as base. This is my conjugate acid, which means here water's acting as an acid, and this is my conjugate base. Base to conjugate acid, acid to conjugate base. What about trimethylamine? Students get really tripped up because they're like, I've never learned that. That's probably correct. But you can do it because you can recognize that you've got this nitrogen hanging out here. When it says amine, it means like ammonia. Amine means it has a nitrogen with a lone pair. Which also means it's a base. So CH3, 3N, plus water, equilibrium arrows, CH3, 3NH plus, it gained a proton, plus OH minus. This is acting as your base, which makes this the conjugate acid. This is acting as your acid, which makes this your conjugate base. Okay, what about carbonic acid? You guys should know what carbonic acid is. First of all, it's acidic. But if you don't remember what it means, ic acid means it came from 8. Carbonate is CO3 2 minus. So carbonic acid is H2CO3. 5H2CO3 in solution, it can only do one thing. It can only give up a proton. Can't do anything else. Draw out the Lewis structure, and you're going to see the Lewis structure looks like this. So it can lose up to 2 protons. It's a diprotic, but it can't do anything else. It can't gain any. This in water, equilibrium arrows, forms bicarbonate, HCO3 minus, plus H3O plus. Some students may say, well, why didn't you just go to carbonate? Because this is looking at the conjugate acid-base pairs, which is the movement of 1 proton, not 2. This is acting as my acid, which makes this my conjugate base. It's acting as my base, which makes this my conjugate acid. If I had bicarbonate, that is HCO3 minus. Bicarbonate can do both. Bicarbonate is like water where it's amphiprotic. It can be either an acid or base, so let's treat it as both. And acidic, if bicarb acts as an acid, H3CO3 minus plus water, acting as an acid, it would donate that proton, so it would form carbonate and hydronium. This is the acid. This is the base. Conjugate base. Conjugate acid. But it can also act as a base. equilibrium arrows. It can act as a base by accepting that proton from the water, forming carbonic acid and hydroxide. Making this the conjugate acid and this the conjugate base. So again, this one's amphiprotic. You can do both, just like water. What if I looked at carbonate? Carbonate is CO3, 2 minus. Doesn't have any protons, so it can only act as a base. Put that in water. Equilibrium arrows. I get bicarbonate and hydroxide. Got my base, making this my acid. The water's an acid because it gave up the proton to the base. This is my conjugate acid. And this is my conjugate base. Okay. Fill in the table below. I guess I could have left that there. If I look at this table, remember how these are interconnected? Remember, pH is the negative log of H3O plus concentration. POH is the negative log of hydroxide. pH plus POH equals 14.00. So with just that, I'm going to fill in the end here. If I know pH is 3.75, that means POH has to be 10.5. If I know POH is 5.5, that means my pH has to be 8.45. I can also figure out the other values really quickly from that as well. But I can also interchange these. I know that H3O plus concentration times, that thing is driving me nuts, hydroxide concentration is 1.00 10 to negative 14. So to get the values in here, I can interchange them that way. I can also take advantage of these the equations over here that I already wrote down, these ones. I can take advantage of those, knowing that my H3O plus concentration is equal to 10 to the negative pH, and my hydroxide concentration is equal to 10 to the negative POH. Okay, so with that in mind, I'm going to go ahead and fill in the first row. 3.8 times 10 to the negative 8 molar concentration for hydronium would give me 2.6, 10 to the negative 7 for hydroxide, 7.42 for pH, and 6.58 for POH. The second column, or the second row, having a 7.6 times 10 to the negative 2 for hydroxide means I'm going to have a really weak hydronium concentration. It means it's pretty basic. I'm going to have 1.3, 10 to the negative 13 for hydronium. My pH, should look at the right column, pH is 12.88, which I said is going to be really basic, and it is. And my POH is 1.12. And then the last two here, my third row, this is 1.8, 10 to the negative 4, and 5.6, 10 to the negative 11. I kind of expected. I'll talk about that in just a sec. And then here, 3.5, 10 to negative 9, 2.8, 10 to negative 6. So again, pH is a measure of how many protons I have in solution. This is near neutral, meaning that the species are the concentration of hydronium. So this value is near neutral. It's a little basic, meaning there's more hydroxide than hydronium, but near neutral. And these are similar. Still more hydroxide than I have of hydronium, but still near neutral. This is a very basic pH, so I expect a lot more hydroxide than hydronium. I see a lot more hydroxide than hydronium. This is a pretty acidic pH. I expect a lot more hydronium than a hydroxide. I expect a small hydroxide concentration and a large hydronium concentration. Again, what I see. This is more basic, not super, super basic, but definitely basic. More hydroxide than hydronium, more hydroxide than hydronium. So they are all interconnected, interrelated to one another. Number 18, what is the pH of a 0.055 molar nitric acid solution? Nitric acid is HNO3. that is one of my strong acids. When I put this into water, it dissociates 100%, so I just have a single-headed arrow, forming H3O plus ions and nitrate ions. So hydronium and nitrate. But that means if I have a 0.055 molar concentration of nitric acid, that gives me a 0.055 molar HNO3 solution and a 0.055 molar nitrate solution. This is a spectator. So only this is going to affect my pH. pH, negative log of H3O plus. So negative log 0.055. And I get an answer here of 1.26. Number 19, what is the pH of a 0.028 molar sodium hydroxide solution? Sodium hydroxide, I know, is NaOH. I also know this is a strong base. Again, don't put plus water on your strong bases. It just makes it more confusing. We have it, we're emphasizing the water by putting aqueous here. NaOH splits up into Na plus ions and OH minus ions. If I have 0.028 molar here, that means I have 0.028 molar here, but this is a spectator. It's the conjugate of sodium hydroxide, which is a strong base. It doesn't want to do anything in solution. And 0.028 molar for the hydroxide here. I'm going to find POH first because for me that's easier. Again, you can go H3O plus times OH minus is equal to 1.0010 negative 14. You can use that to find hydronium concentration first, then find pH. I like going through POH. POH is the negative log, 0.028. I get a POH of 1.25. I know my pH plus my POH has to equal 14, which means my pH has to be equal to 12.75.
Number 20, what is the pH of a 0.028 molar strontium hydroxide solution? So first thing you need to remember is what is the formula of strontium hydroxide? Strontium, Sr, it is a group 2 metal, so it needs 2 hydroxides for every 1 strontium. That's important, again, because it's going to determine how it's going to break apart in solution. If I put this into water, strontium hydroxide, 100% dissociation. Why? It's a strong base. Remember, we can look at our periodic table and find our 8 strong bases. So strontium hydroxide is a strong base. It dissociates into strontium ions and hydroxide ions. Notice for every 1 mole of strontium hydroxide, 1 mole of strontium is formed and 2 moles of hydroxide are formed. That's important because we need to think about the number of moles we have of something to figure out the molarity. If I have a 0.028 molar solution of strontium hydroxide, that means I also have a 0.028 molar solution of strontium, but I have 2 times that, or 0.056 molar for the hydroxide ions. Why? Because I have twice as many hydroxide. When that strontium hydroxide breaks apart, it breaks up into, for every single strontium hydroxide formula unit, it gives me 1 strontium ion and 2 hydroxide ions. So I have double the amount of hydroxide. And that matters when you're finding the pH. So again, I'm going to go through POH. It's easier for my brain to see. Lowercase p just means negative log of whatever follows. So this is the negative log of the hydroxide concentration. So negative log of that 0.056 molar. This gives me a value of 1.25. But I want pH. This is POH. Number one, I should recognize it is a base. The pH needs to be above 7. Number two, I need to realize what I just calculated, which was POH, and I really want to solve for pH, so I need to convert to pH. Remember, pH plus POH is equal to 14.00. Therefore, my pH here is equal to 12.75. So it is basic as I expected for the pH of this base solution, which again, it should be. If I didn't get a basic pH, I did something wrong in the calculation. What number 21? What is the pH of a 2.75 times 10 to the negative second molar concentration of acetic acid? When I put things in scientific notation like that, saying 10 to the negative 2, that's just to be annoying, to be honest. Like, that's just the way my brain sees it. It's just being annoying. Really, just remember that's the same as 0.0275 molar. Some students like it better in scientific notation, some students don't. It's really your preference. I could care less which one you write it as, okay? But some students need to rewrite it as this. Apologize, I have kittens that want to be everywhere what I'm doing. Um, but some students want to see it in scientific notation, some students don't. I have zero preference. I'm gonna go ahead and remove this just because I need space. So I need to also recognize that acetic acid is a weak acid, which means it only partially ionizes. Only some of the acetic acid molecules in solution will give up a proton, not all of them. So I have to use the Rice chart. I also should know the formula of acetic acid. CH3COOH, or if you want to write it as, C2O2H4 or HC2H3O2, I don't care as long as it's the right formula. Put it plus water. If you do not want to write the plus water, that's fine. If you write plus water, you have to write H3O plus on the product side. If you do not include the water, you have to write H plus. Remember, H plus and H3O plus mean the same thing. It's just a convention thing. Writing H plus is slightly faster. Make sure to include your phases. Okay, you're set up your Rice chart here. So RICE, R for reaction, I for initial, C for change, and E for equilibrium. Initially, I have 2.75 times 10 to the negative 2 molar acetic acid present. Water is a liquid, so it doesn't factor into the math at all. The water is the solvent, I should be specific. Water is the solvent in this case, so therefore the concentration of water will remain relatively unchanged for the reaction. I don't have any acetate to start, and I have virtually no hydronium. Again, virtually because I do have some hydronium present from the autoionization of water, but that is at a concentration of 10 to the negative 7. This concentration is greater than that, so the hydronium that's going to affect the pH in the solution is due to the acetic acid, not the hydronium or the water autoionization. Change, I've got minus x plus x plus x. Again, minus because this is the only thing present at the start. It's the only thing I have, so it's the only thing that can react, okay? I don't have any hydronium or acetate, so they're going to be produced. At equilibrium, I get 2.75, 10 to the negative 2, minus x, and x. Now, when you're writing these out for any exams or quizzes, you should be writing out the K expression with letters and with the variables. The K expression here is CH3COO minus, H3O plus, and CH3COOH. Notice this is for the acid ionization. I know that because one, acetic acid is what's ionizing, but two, I'm producing hydronium, so I know I need to use the Ka value. So I look on the front page and I find the Ka value of acetic acid, and I find it to be 1.8 times 10 to the negative 5. Now I'm going to go ahead and plug in my variables from my equilibrium step. So from the step down here, I'm going to plug these in to my K expression. This will give me x squared over 2.75 times 10 to the negative 2 minus x. I truly don't know if I can ignore this x yet or not, but I'm going to try, and I'm going to check the assumption. So I'm going to assume that x goes to 0, and then I'm going to do the math on it and see if it actually is, in fact, negligible. Okay, shrink that to get it out of our way. Solve for x here. And when I solve for the x up here, I get an x value of 7.04. My sig figs are right here because I had two sig figs right here. I had three here, but my Ka value had two sig figs. So two sig figs, I'm going to underline my sig figs, times 10 to negative 4 molar. I'm going to find the pH of that solution because, again, what does X represent? X represents the hydronium concentration at equilibrium. So that means I can go straight to pH here. Negative log of 7.04 times 10 negative 4 molar. Now, my final answer here needs to have two sig figs. So remember, when you are in the log scale, what I get out here is 3.15. This is due to the log. Anything after the decimal place is my sig figs. So 3.15 is two sig figs. I do have to check my assumption here to make sure I'm correct in ignoring that x. And so I'm going to erase the strong base stuff over here to do the assumption over here. Remember, you check the assumption the same way that you figure out how much ionizes. You're going to take the percent dissociated, so x divided by the part it broke off from. 2.75, 10 to the negative 2. That value of x was 7.04, 10 to the negative 4, and multiply that by 100. It's the whole part over whole times 100%, okay? If this is less than 5%, it's a valid assumption. This is also, though, how you figure out how much ionized. The answer here is 2.56, sig figs are here, percent, which could be rounded to 2.6%, and my assumption is valid. But what this also means here is that in this solution, 2.6% of the acetic acid molecules will give up their proton. So it's not just that it's telling me my assumption's valid, it's actually telling me a lot about the system itself. Number 22, what is the pH of a 0.125 molar nicotine solution? I need to recognize that nicotine is a base. How do I know it? I see this nitrogen right here, and this nitrogen doesn't have, this is not a salt. It's clearly not a salt. I don't have an anion, a counter anion here to balance our charge. Okay, so it's definitely not a salt. It also does not have a positive charge on it. Therefore, I can tell very quickly this must be a base. So nitrogen and not a salt, i.e. no cation anion combination. And it has no cation. Where it has a positive charge on the nitrogen. So I know it's a base. So I know what it's going to do in solution. It is going to accept a proton from water. It's going to steal one. So let me temporarily move that out of the way. Okay, so if I've got C10, H14, and 2, I got a weak base. I'm putting it in water. If you have a weak base, always write plus water. Okay, you have to show where that proton is coming from. Equilibrium arrows. How do you know what your product is? This can throw students off. A base accepts a proton. So it's got to have one more proton, but when it does that, it gains the proton but no electron, so it gains a positive charge with it. C10, H4, or H14, I can read my own writing, N2, H plus. This H on the end is the H it gained, plus hydroxide. Set up your rice chart. Initially, I have a 0.125 molar solution of nicotine. Water is my solvent, so it's not going to factor into here at all. My conjugate acid, I don't have any of it to start. and I have approximately no hydroxide to start. Again, the amount of hydroxide in natural or native water, native pH water, so just pure water, is 10 -7. This is higher than concentration, so anything I produce here should be higher than what water naturally has. Minus x plus x plus x. Minus for the reactant side because I'm consuming it. Some of those are reacting to pull proton, and then positive on the product side because that's what I'm producing. 0.125 minus x, x, and x. Go ahead and set up your K expression. And I've got C10, H14, N2H plus times hydroxide over C10, H14, N2. I know this is the KB because I'm producing a base. So I have to be using KB here, okay? If I gave you KB, you could use the number straight out. If I didn't, you'd have to use Ka to find KB. Here, I'm giving you guys a KB value, 1.0 times 10 to the minus 6. Plugging our values from the table, x squared over 0.125 minus x. Again, I'm going to assume that this x is negligible, which simplifies the math. That makes it x squared over 0.125, okay? And solve for the x in the numerator there. When I solve for x, I get 3.54 times 10 to the 4. I'm just underlining the sig figs there at the 5. The sig figs are limited by my KB value here. But again, remember what that value of x represents. X represents my hydroxide concentration in my solution. So my hydroxide concentration is 3.5 times 10 to the 4. I'm going to find my POH, negative log, 3.54 times 10 to the 4, gives me a value of 3.45. Again, I need two sig figs here. These are my sig figs. This is due to the log. So the number in front is due to the log. The actual decimal places are my sig figs. But that is my POH. I need pH. pH plus POH equals 14. My pH is 10.55. Now, I should check my assumption because I did make one. Again, checking the assumption is the same thing as figuring out the percent ionization. So it's my part over my whole. My part is the part that dissociated. 3.54 times 10 to the 4 molar. And how much I started with was 0.125 molar. Multiply that by 100%, and I get 0.283%. It's less than 5%, so my assumption is valid. Therefore, the pH of the solution would be 10.55. Okay, the amount that's dissociating is really small. Less than 1% is actually stealing a proton. So that little bit, I can, assuming that X negligible is absolutely valid. If I subtract that X value 3.54 times -4 from the actual concentration of the original nicotine, it wouldn't make a statistical difference to the value. Let's go ahead and work the next one. Number 23, a 1.8 molar solution of unknown monoprotic weak acid has a pH of 3.42. What is the Ka value for this acid? Well, I don't know what the acid is, but that doesn't really matter. I'm going to just use Ha to represent the acid. It's monoprotic, meaning it has one proton. It's a weak acid, so I know it's going to undergo an equilibrium with water to form the conjugate base and H3O plus. I don't have to know what the acid is to do that. Set up my rice chart. I'm told that I'm starting with a 0.18 molar solution. Water is negligible, and I'm not told about any conjugate base in solution yet. And my hydronium concentration is approximately 0. I am told though that normally I would say, minus x, 0.18 minus x, plus x and x, and solve for Ka, but I'm trying to find the Ka value. So with that in mind, like we normally do, Okay, set up your Ka expression. Conjugate base, hydronium, weak acid, x squared over 0.18 minus x, but I don't have a value for Ka. That's what I'm trying to find. So instead, what I do is I take advantage of the other piece of information this question has. This question is telling me what other piece of vital information? pH of 3.42. Remember what pH is. pH, the negative log of the H3O plus concentration. This equals 3.42. That means I can undo that. That means that my H3O plus concentration is equal to 10 to the negative 3.42, which is 3.8 10 to the negative 4. There's a molar, there's concentration. Remember, this is in a log form, so these are the 2 sig figs, so 2 sig figs. I use the pH to find the hydronium concentration, but remember what that represents. That represents X. I know X. X is equal to 3.8 times 10 to the negative 4. I can plug that into my Ka expression. So 3.8 10 to the negative 4 squared, 0.18 minus 3.8 times 10 to the negative 4 is equal to my Ka value. And I get a Ka value here of 8.0 10 to the minus 7. So just kind of working backwards what you guys are used to doing, seeing it from the other direction. Let's see, what is number 24? A 0.25 molar solution of unknown weak base has a pH of 9.75. What is the value of Kb for this base? Okay, similar, very similar to what we just did, just slightly different things we have to think about what we're doing here, okay? So base, a weak base, I'm just going to use the letter B for base. Weak bases go into water, and they steal protons. So it's going to form a conjugate acid and hydroxide. I'm told it's a 0.25 molar solution. And I just set up my rice chart like I normally would. So write out the K expression here. I know it's Kb because I've got hydroxide. And I know that if I put in my values for my equilibrium, I would have x squared over 0.25 minus x. How do I figure out what to plug in here? I'm going to take advantage of that pH again. But I need the concentration of hydroxide. I can do this one of 2 ways. I can undo the pH and find the hydronium concentration. I then can remember that hydronium times hydroxide equals Kw at 25 degrees C, which we will assume these questions are at unless otherwise stated, and find hydroxide and then plug it in. Or I can go, pH to POH and undo that to find hydroxide. It doesn't truly matter which one you do. I just did it this way instead because it's faster for me. So if my pH is 9.75, that means my POH is 4.25. My hydroxide concentration, 10 to the negative 4.25, equals 5.6 to 10 to the negative 5. 2 sig figs, because again, the sig figs are here. I'm just going to underline them. So 5.6 times 10 to the negative 5 is actually sig fig correct. And plug that into my Kb expression. Kb equals 5.62, 10 to the negative 5, over 0.25 minus 5.62 times 10 to the negative 5. And I get out in a value 1.3 10 to the negative 8 for my Kb value. So again, very similar to what we did in number 23, just looking at Kb instead of Ka. Number 25, given that the Ka for hydrocyanic acid is 4.9 times 10 negative 10, what is the Kb for cyanide? Yeah, what is hydrocyanic acid? Hydro and ic means it came from ide. So it came from cyanide. Cyanide is Cn minus, so hydrocyanic acid is HCN. These are conjugates. This is the acid form. This is the base. I know that Ka times Kb equals Kw for conjugates. I know that Kw is equal to 1.00 10 to the negative 14. So I'm just going to solve for it. Kb, 1.00 10 negative 14, divided by 4.9, 10 to the negative 10, gives me a value of 2.0, 10 to the negative 5. So again, just taking advantage of this relationship, which is valid for any conjugate acid-base pair. Number 26, phosphoric acid is a polyprotic acid with the following dissociation constants: Ka1, Ka2, and Ka3. Determine the Kb values for phosphate, hydrogen phosphate, and dihydrogen phosphate. Now, let's think about what this means. A phosphoric acid is H3PO4. Its first dissociation is losing one proton and forming dihydrogen phosphate. Dihydrogen, so it's two hydrogens and then phosphate. The Ka for this thing is 7.5 10 negative 3. It's the first one lost. So Kb, I know that value of Kw. Kw is 1.00, 10 to the negative 14. And I know Ka times Kb is equal to Kw. So I'm just going to undo that. So for phosphate, or for dihydrogen phosphate, the Kb value would be 1.3, 10 to the negative 12. If I look at the second dissociation, that means I am taking dihydrogen phosphate and removing a second proton. This forms another hydronium ion, or H plus for simplicity, plus hydrogen phosphate. When I say hydrogen, it just means a single hydrogen versus dihydrogen. The Ka value for the second dissociation is 6.2 times 10 to the negative 8. Notice it's much smaller. It's much harder to lose that second proton. The Kb value here is Kb, Ka. The Kb value here, 1.6, 10 to the negative 7. And the last one is the last association, which is taking that hydrogen phosphate and taking its last proton away. And again, the Kb means the opposite direction. So the Kb, I don't have a lot of room on the slide, but I'll write it in just a sec. But if I wanted Kb for this one, this would be 0.24. So this, as written, is a Ka expression. What this is saying is I am taking this compound, dihydrogen phosphate, putting it in water, and it's acting as a base and reforming H3PO4. That needs that Kb value. This one is saying I'm taking that hydrogen phosphate, putting it into water, and it's acting as a base, and it's forming that dihydrogen, plus hydroxide. It's forming dihydrogen phosphate and hydroxide. This one down here is saying I'm taking phosphoric acid, putting it in water, I'm putting phosphate in water, and I am forming hydrogen phosphate and hydroxide. So not only is Kb the opposite process, it's thinking about the opposite reaction. It's thinking about that conjugate base now, because it's Kb, reacting with water to pull off a proton and form hydroxide. Number 27, ascorbic acid H2C6H6O6 is a diprotic acid with the following dissociation constants: Ka1 and Ka2, 8.0 times 10 negative 5 and 1.6 times 10 negative 12, respectively. Consider a zero point 0.1 molar solution of ascorbic acid. What is the hydronium concentration, pH, the HC6O, C6H6O6 minus, and C6H6O6 2 minus in the solution? So the hydrogen ascorbate and the ascorbate in the solution. So this one's going to be a long one, so I'm going to need to find some space. Okay. First up, let's just think about what this means, what each of these things mean. This is losing the first proton. This is losing the second proton. So let's go ahead and write it out. Try to lose that first proton. H2C6H6O6 plus water forms HC6H6O6 minus plus H3O plus. Again, I've lost one proton. I started off with a 0.1 molar solution here. I didn't start off with any of this, and I have approximately none of this. Write out the Ka expression here. It's going to be equal to HC6H6O6 minus times H3O plus concentration divided by the ascorbic acid. Okay, so let's go ahead and plug in what we know for a Ka expression. Try to not delete this yet. This is equal to x squared over 0.10 minus x. And our Ka value for the first association is, it tells me in the question. Sorry, I'm trying to read my computer screen for the actual answers and then write on the iPad for the work for you guys. Okay, 8.0 times negative 5. It's a pretty good chance we'll be able to assume the first x is equal to 0 or goes to 0, but we do need to check it just to be safe. So I will check this in just a sec by assumption. If I solve this out though, I get an x squared value or an x value of 0.0028 molar, and I need to check that assumption. 0.0028 molar divided by 0.10 molar times 100% gives me 2.8%. My assumption is valid. That makes my life easier when to do the quadratic formula. But that means that I'm starting my next rice chart, because I do need a second one, because I have a second association, with a starting concentration of the, I'm going to write these down here, HC6 6 minus concentration initial. This is the initial after the first association, is equal to 0.0028 molar. And I'm just writing these down because I have to erase everything above because I'm not going to have room. And I'm starting off with a hydronium concentration initial here as well of 0.0028 molar. Again, the x here and the x here represent these, and that's what I just solved for. The equilibrium concentration of 1 is the initial concentration of the next table. So I'm going to erase this top because I need the space back. Now I'm looking at the second dissociation. So we've used this value. Now we're going to go ahead and use this one. What that represents is the second dissociation. I've got the conjugate base of ascorbic acid, but remember this is diprotic or not diprotic, amphiprotic or amphoteric, whichever way you want to say it, meaning it can act as an acid or a base. And so this reacts with water, donating its second proton, forming C6H6O6 2 minus and H3O plus. I'm starting off with this concentration, 0.0028 molar here, and 0.0028 molar here. You guys are used to it being zero there, but it's not zero there because I didn't have any of it to start. It's not zero yet, okay? I actually do have some. Water is my solvent, so it won't do anything, it won't affect its concentration. It's staying constant throughout this whole thing. Minus x plus x plus x, x, and 0.0028 plus x. I'm going to go ahead and shrink that down. And set up my K expression. It is still Ka because I'm still acting as an acid, or the species is still acting as an acid, still producing hydronium. So H3O plus. And my second Ka value is 1.6, 10 to the negative 12. And plug in what we have on the table. In my numerator, I have x times 0.0028 plus x over 0.0028 minus x. Now I've got x being added, subtracted, numerator, and denominator. So I'm going to assume that it's smaller in both cases. If it's smaller in one, it's going to be smaller in the other because the value is the same for the value it's being added to or subtracted from, right? So it doesn't matter. It doesn't much matter. I'm still going to check assumptions, but I'm going to assume that this x goes to 0 and this x goes to 0. Why? Because that really simplifies my math. That says 1.6 times 10 to the negative 12 is equal to x times 0.0028 divided by 0.0028. That gives me an x value, 1.6 times 10 to the negative 12. And again, check your assumption there. I'm going to write that down here. My assumption, 1.6 10 to the negative 12. I assumed it was smaller than 0.0028. It gives me 5.7 and the minus 8, which means, and that is percent, which means my assumption's valid. But again, what does that value mean? What does x represent? X is representing a couple things here. X represents the amount of hydronium being added to the existing hydronium in solution after the second dissociation. X represents the amount of the C6H6O6 minus in solution after the second dissociation. Now I can answer the questions. I want, let's see, hydronium, pH, HC6, H6O6 minus, C6H6O6 minus in the solution. Concentration of each one. Okay. Oh, I don't have any space where to write this. Okay, I'm gonna just erase this up top here. I'm gonna keep this, remember what this represented is the X over here. That means that my hydronium concentration in the solution is equal to 0.0028 plus 1.6 10 to the negative 12, which really equals 0.0028, and it is concentration, so it is molarity for the units here. That little bit more of dissociating at the end is not changing the concentration at all. My pH is next. pH is the negative log of that value. Gives me a 2.55 for pH. No surprise, it's an acid. I expect the solution to be acidic. my, let's see, H6O6 minus concentration is equal to that 0.0028 minus 1.6 times 10 negative 12, which is still 0.0028 molar. And C6H6O62 minus concentration is equal to 1.6 times 10 negative 12. So I've answered all of it. I figured out all of them. Number 28. Determine whether the following salts are acidic, basic, or neutral. Okay, first you gotta figure out what they are. So ammonium chloride is NH4Cl. I know they're salts, and I'm going to assume that they're all going to be soluble in solution. Okay, we don't deal with partially soluble until the next chapter, so I'm going to assume they're all soluble. If I put NH4Cl into solution, into water, this dissociates into ammonium ions and chloride ions. So I need to think about, if I mix this with water, is this going to do anything? If I have this mixed in water, is this going to do anything? This one isn't going to do anything. Chloride is a spectator. It is it causes the solution to be neutral. It's the conjugate base of a strong acid, which means it's a very weak base. It's a very stable base. It's so stable as a base that it's not going to pull a proton off the water. The NH4 plus, though, this species is the conjugate acid of NH3. How do I know that? It's got a positive charge, so it gained a proton. And if it gained a proton, if I took it away, it'd be NH3, so it's ammonia. Ammonia is a weak base. So it's a weak base, which means that ammonium is a strong enough conjugate base to affect the pH of the solution. The solution will be acidic, specifically because of the ammonium. The chloride isn't doing anything to it. Okay, what about potassium nitrate? KNO3. I put KNO3 in solution. Keep in mind when I'm separating my salt here, this is all a single-headed arrow here, they're all completely dissociating. K plus and NO3 minus. If I add the K plus to water, what's going to happen? Nothing. K plus came, it's the conjugate acid of a strong base. It came from KOH, which is a strong base. The potassium ion is very, very stable in solution, meaning it is a very weak acid. It can't do anything to cause a solution to form an acid. We have talked about metals. Sorry, we have talked about metals causing solutions to be acidic because, and we'll talk about that in the next example too, the aluminum chloride. The metal ions are surrounded by water molecules, um, and it allows one of the protons and one of the water molecules to be removed, causing acidic solution. Potassium cannot do that because of the size to charge ratio. The charge on sodium or potassium, the charge on potassium is weak enough; it's only a +1 charge, and the potassium ion itself is just a bigger ion. So the charge to size ratio is not conductive to it actually allowing a water molecule to lose one of its protons. It's not polarizing that bond enough. So this causes this acts as a spectator in solution. If I said nitrate in water, it's the same thing. Nothing happens. Nitrate is the conjugate base of a strong acid. Comes from nitric acid. It is a conjugate base. It is very stable base, meaning it is a very weak base. It is very stable as nitrate. It's not going to pull a proton back off of that water. So it is also a spectator, which means this pH will be neutral. What about sodium cyanide? NaCN. In water, this dissociates into sodium ions and cyanide ions. So again, if I mix this with water, I mean, in order for them to dissolve, they have to be in water. So this is with water. What's going to happen? Nothing. It's going to act as a spectator. Can't spell. The sodium ion is the conjugate acid of a strong base. It comes from sodium hydroxide. Metal ions form acidic solutions when the metals are small and highly charged. So only has a +1 charge, and its charge to size ratio is not conductive to it being able to form an acid. Again, it has to have a small enough radius on the ion itself and a large enough charge to attract water molecules in such a way that the hydrogen oxygen bond in the water molecule is polarized enough that the water can lose a hydrogen to another water molecule in solution. That will not happen with any group 1 or group 2 metal cations. It just will not happen. So they act as the spectator, they do not affect pH. If I look at cyanide, though, this is cyanide is the conjugate base of a weak acid. So in solution, this will form HCN and hydroxide. It's the formation of the hydroxide here that makes the solution basic. The last example we have here is aluminum chloride. You need to recognize aluminum chloride AlCl3. This gives me Al3 plus ions and Cl minus ions, 3 of them, in solution. This is a spectator. And this is not. The Lewis, this compound of Lewis acid. Let's go back through what's happening here. When the aluminum goes into solution, okay, the aluminum chloride goes into solution and the ions immediately disperse. I've got aluminum ions and chloride ions. How do things dissolve in solution? Remember, they dissolve because the water molecules come in and they surround the ions and pull them away from the other ions. The aluminum is surrounded by water molecules, and specifically the oxygens orient themselves towards the aluminum. Oxygens because of the positive charge on the aluminum and the partial negative on the oxygen. I'm going to run out of room here. But six water molecules will surround that oxygen. Why 6? Think about it like a cube. Okay, there's 6 sides to a cube. Just think about it like a cube. We know it's 6 from experimentation. When it's a small enough ion, it can fit 6 water molecules around it. So aluminum ion has split around here and surrounded by these water molecules that are allowing it to be stabilized in solution. That's what's separating away from the chloride ions. The chloride has the same thing happening with water molecules. Remember, there's a huge abundance of water molecules compared to the amount of aluminum chloride here. The chloride ions are being stabilized by the hydrogens on different water molecules, but they're being pulled away from each other. So in essence, I've got aluminum 3 plus forming some kind of attraction with 6 water molecules. It's a single-headed arrow, and this forms a complex of a hydrated aluminum ion. So my aluminum, my 6 waters, and it has a 3 plus charge to it. And it exists only in aqueous solution. Okay? Now, what happens on here is the attractive force between the oxygen and the aluminum. The oxygens here are very attracted to the aluminums. Okay, make sure I do them all. Another water molecule comes along, and because of the attractive force between the oxygens and the aluminums, these oxygens aren't treating their own hydrogens very well. So these bonds between the oxygen and hydrogen here are weakened. These bonds here are already polar bonds, right? But they're becoming weakened even more so because the oxygen's pulling all of its electron density to attract that aluminum ion in the center. So a different water molecule comes along and says, I'm going to go ahead and steal that proton from you because you're not, it's such a positive proton. It has such a positive partial charge to it because the oxygen's kind of ignoring it anyway. And the electrons then from this bond here stay on the oxygen atom. So what we form is, and this is a tetrahedral compound, but I'm not going to draw a tetrahedral right now. Okay, this forms, and this has lost one proton, giving a negative charge. So what happens in the reaction is that the aluminum H2O6 3 plus aqueous reacted with a different water molecule and lost a proton. And this is an equilibrium. Now I only have 5 water molecules and 1 hydroxide. Again, the 1 hydroxide right here. And the charge has gone down by 1 because I still have the +3 on the aluminum, but now I have a -1 on the oxygen, overall +2 charge. So it forms this aluminum water hydroxide compound, but it also forms hydronium ion. And this is what's causing it to be acidic. The presence of that hydronium ion causes the solution to be acidic. And how much depends on the concentration of the species. But that's why small, highly charged metal cations can be acidic. They're doing this. This is forming. You need to be able to understand this and explain it. But also, when I say small, you won't see this happening with group 1 or group 2 metal ions. So, sodium, potassium, rubidium, lithium, cesium, not going to happen. Group 2, magnesium, barium, strontium, calcium. I don't remember what else is in group 2 without the periodic table in front of me. But it won't happen because they don't have a small enough size to charge ratio. First of all, group 1 is only a +1 charge. It needs to be at least a +2 charge to cause this to happen. Minimum +2. Okay, but it's not going to happen for the group 2 metal ions either, your alkaline earth metal ions, because the ions themselves are still too large to cause this to happen. We need a small charge to size ratio. What I want you to think about is, where is the positive charge residing? In the nucleus, right? That's where the protons are. You've got electrons blocking the nucleus. We talked about effective nuclear charge in first semester. And so you've got these electrons in their energy levels outside of the nucleus, blocking that nucleus has a positive charge. That positive charge is trying to attract water molecules outside of that ion, even further out. So I've got to have it small enough so that those water molecules on the outside can be super attracted to it to weaken that bond with a hydrogen atom in the water molecule to allow a different water molecule to come along and take that proton away. All of that to say, this is acidic. It's small. It's not group 1 or group 2 metal. It's highly charged. It's a +3. +2, +3, +4 will do it. So, what is the pH point of a 1 molar aluminum chloride solution? Well, I just ran through some of these reactions, but I need you guys to think about what these reactions mean. If I have aluminum chloride, AlCl3, what I really have, single-headed arrow, is Al3 plus and 3 moles of Cl minus in solution. So if I had 1 molar here, I now have 1 molar here and 3 molar here. But again, this is a spectator, so I don't have to care. I don't really care what the spectators aren't doing. They're not doing enough in this class, at least, that we have to care. This is this is what matters. The aluminum 3 plus then reacts with 6 water molecules, single-headed arrow, forming the hydrated aluminum ion. Aluminum H2O6 3 plus, and it is aqueous. Now I care about this species. I had 1.0 molar here, which means I still have 1.0 molar here. That hydrated aluminum reacts with a water molecule, and this is an equilibrium arrow, forming H3O plus, which is what caused the solution to be acidic. And I'm gonna run out of room here. Al for aluminum, H2O5, because I don't have 6 waters anymore. One of them lost a proton. OH, and 2 plus. The charge went down by 1 because I lost 1 proton, left behind the electrons. Now I can set up my race chart. I have 1 molar here, minus X, 1.0 minus X. Water is my solvent. Approximately none here, plus X and X. I have none of this, plus X and X. Set up my Ka. You would have to be given the Ka, so it would be on the first page of your exam. You should be able to write the Ka expression. My Ka expression here, products over reactants. My aluminum with my 5 waters, my hydroxide and my 2 plus charge, my hydronium concentration, and my original hydrated aluminum salt, or hydrated aluminum ion. The Ka for this compound is 1.4, 10 to the negative 5. Plug in our values from the table, x squared, 1.0 minus x. I am going to assume that x goes to 0, solve for x, and I get 0.0037. But again, remember that represents the hydronium concentration at equilibrium. So that is molar, and that is equal to H3O plus. We should check our assumption just to be safe. I have 0.0037 molar divided by 1.00 molar times 100%. This gives me 0.37%. So it is a valid assumption, and I can move forward. Now that I have the hydronium concentration, I can find the pH. pH is the negative log, 0.0037. Again, 2 sig figs here because the 1.0 here and the Ka as well had 2. So I need 3 decimal places. 2.43. I expected it to be acidic for aluminum chloride, and I found it to be acidic. And for this concentration of aluminum chloride specifically, it would be 2.43. Number 30, what is the pH of 1 molar sodium acetate solution? Sodium acetate, NaCH3COO. I have to recognize that this is a salt. How do I know that? I see that I have a cation and an anion. Therefore, it's a salt. Truthfully, I just recognize it as a salt because I see that it's not just an acid or base, it's a salt. It's either going to be an acid, base, or salt. This is a salt. So I have to think about what's happening in solution. If I have NaCH3COO, that splits apart entirely into sodium ions and acetate ions. So if I have a 1 molar solution here, I have 1 molar sodium ions and I have 1 molar acetate ions. But this is my spectator. How do I know that? It's conjugate acid of a strong base. It's a group 1 metal cation. It's not doing anything. But I know that this came from acetic acid. So this is a conjugate base of a weak acid. How do I know that? Well, it's a negative charge. So if I give it a proton, I would get CH3COOH, which I recognize as acetic acid, and I know acetic acid is weak. It's not one of my strongs. I mean, I do technically have it memorized as weak, but even if I didn't, it wouldn't be one of the strongs I have memorized. So I'm going to look at how CH3COO minus acts in solution. When put into water, this acts as a base. It is going to take that proton back from the water molecule and form acetic acid and hydroxide. Set up my rice chart. Initially, I have 1 molar sodium acetate. I don't have any acetic acid at the start. The question does not say I have any present. And my hydroxide concentration is approximately 0. So change minus x plus x plus x, 1.0 minus x, and x. Set up my K expression. My K expression has got acetic acid times hydroxide over acetate. Because I've got hydroxide, I know I've got Kb. Most likely I only gave you the Ka value for this because I probably didn't give you Kb because it comes from acetic acid. The Ka of acetic acid is 1.8, 10⁻⁵. I know Ka times Kb is 1.00, 10⁻⁴. So I'm going to rearrange that equation, solve for Kb, and I'm going to find that my Kb value is 5.56, 10⁻⁻. I'm going to underline where my sig figs are. This gives me 5.56, 10⁻⁻. X squared over 0.10 minus x. And I'm going to assume that x goes to 0, simplifying this equation. Solve for x, and I get 2.3, sig figs are there, 6 times 10⁻⁵. But remember what x represents here. X represents my hydroxide concentration. POH, negative log 2.36, 10⁻⁵. I need 2 sig figs, so I need 2 decimal places, 4.63. pH is 14. pH plus POH equals 14. So the pH is equal to 14.00 minus POH, a value of 9.37. I expect this to be basic pH because it is a salt and it is the conjugate base of a weak acid, so I expect it to be basic, and it is in fact basic, so I'm assuming math is correct. It is correct, but I'm just saying it's a good way to check yourself. About the next one. What is the pH of a 1 molar methyl ammonium chloride solution? You need to recognize it as a salt. You need to separate this out, okay? Even if you don't recognize exactly how to separate this out, by saying salt, you should be able to recognize chloride. Therefore, the other species has to have a positive charge because they have to counterbalance each other. I have a nitrogen-containing compound with a positive charge. That is an acid. It is a conjugate acid of a weak base. CH3NH3 plus water. It's acting as an acid, so it's going to donate that proton. It can't accept anymore. If you drew the Lewis structure out, you would find that the nitrogen is full. It can't accept anything else. This forms methyl ammonium and H3O plus. 1.0 molar, 0 and approximately 0, minus x plus x plus x, 1.0 minus x, and x. When you set up your K expression, you are doing a Ka here because you are forming hydronium. So you've got methylamine times hydronium divided by the methyl ammonium. Now, I need the Ka value here, and I'm guessing I gave you Kb. I don't actually know what the Kb value is because I didn't write down my own notes. But you would have, remember, Ka times Kb is equal to Kw. So plug that in, and you should find your Ka value to be 2.27, 2 sig figs, I underlined the second 2, times 10 to the negative 11. So 2.27 10 to the negative 11 is equal to x squared over 1.0 minus x. The x here, 4.77, 10 to the minus 6. Sig figs are here. But again, what does x represent? Let's check, because I do tend to forget when I'm doing too many problems in a row. X is representing my hydronium concentration, so I can go straight to pH. Good. So this represents H3O plus. My pH is 5.32. So 1 molar methyl ammonium chloride solution has a pH of 5.32. Okay. Let's see.
Carbon.
Is sodium bicarbonate acidic, basic, or neutral? Well, let's think about this. What is bicarb? Sodium bicarb, NaHCO3, Na plus, and HCO3. So this comes from carbonic acid. Carbonic acid, H2CO3, breaking apart to form HCO3 and a proton, has a Ka value of 4.3 10 to the negative 7. This has a negative charge. This is the second one. So bicarb can act as either an acid or a base. But when I put it into solution by itself, I can do that. Or I can say plus water. And it can reform carbonic acid. The Ka here is 5.6 10 negative 11. That is very, very small. So I found the hydroxide concentration or the hydronium concentration with that Ka. It's very, very small. So this is already 10 negative 7. This is already on the realm of water. If I'm undergoing the second, looking at that second dissociation under these conditions, that's way past what's in water. This is the basic solution. That K value is very, very small. Next time we're going to need some room. When 2.5 grams of an unknown weak acid, H8, with a molar mass of 85 grams per mole is dissolved in 250 grams of water, the freezing point of the resulting solution is negative 2.57 degrees C. Calculate Ka for the weak acid. Okay. It's definitely combining a couple different chapters intentionally to see if you guys can get through it. So let's think about the process here. I know I have an unknown acid, and I know its molar mass. That means I can find the number of moles of acid that went in. Okay? So, number of moles of HA. 2.55 grams. 1 mole is 85 grams. I have 0.0300 moles of HA in my solution. So I've used that. Okay. I've dissolved it in 250 grams of water. Okay, so I can find the molality. 0.0300 moles of HA divided by 0.2500 kilograms of solvent or water, whichever you want to write, gives me a 0.120 molal solution. I know the molality. I'm told that the solution freezes at negative 2.57. Okay. Delta TF is equal to KF times M times I. I know that my delta T here is going to be negative 0.257 degrees C, or sorry, not negative, positive, because again, I'm looking for the change in temperature here, and I'm using water as my solvent. Water freezes at 0 degrees C, so my change in temperature is 0.257 degrees Celsius. Plus, I need it to be positive mathematically because I need to solve for an actual value here. Okay, I can't have a negative thing here. If you get confused, just take the absolute value. You need the delta T to be positive. You're using water, so your KF value is 1.86 degrees C per molal. I have the molality, 0.120 molal, so I must be solving for the I value here. That shouldn't surprise us. It is a weak acid, which means it does not dissociate 100% in solution. So the I value will not be 2. It'll be something less than that. It'll probably be close to 1, a little bit bigger than 1, because some will dissociate, but not very much. Calculate out the I value here, and I get an I value of 1.15. Remember what this means, though? This is the number of moles of particles. So I need the Ka. Okay, well, how am I going to figure that out? I'm going to go ahead and set up a rice chart somewhere. Let's do it over here. I know HA in solution reacts with water to form H3O plus and A minus. So I know that I'm going to use, so let me back up slightly right here. I'm going to use 1 to represent the number of HA part of concentration of HA. It's a placeholder. Okay, separate from the Van Hoff factor. If I had 1 HA, I'd have 0 of this and 0 of this to start. And water doesn't factor in, right? Minus x plus x plus x. At equilibrium, I would have 1 minus x and x. At equilibrium, my number of moles would be x plus x plus x. 1 minus x, sorry. At equilibrium, let me write this over here. At equilibrium, I would have 1 minus x plus x is the number of particles in solution. The number of moles here is related to the concentration. It's all in one system, so I can compare moles and molarity here. But this is equal to 1.15 because this represents the number of particles that I had in solution. We have some HA, and some of it split up to form H3O plus and A minus. How much? X. I don't know what yet, how much yet, but X did. But I also know from the freezing point that this is how many particles I actually have in solution. So I'm going to solve that out. 1 minus x plus x plus x is 1.15. So x is equal to 0.151. And x is the fraction of HA that actually dissociates. Go back up here because I need space again. I just erased something I need. 1 second. Okay. I also figured out previously that I had 0.03 moles of HA in solution. I need to figure out the molarity of the solution here. I know I used 250 grams of water. I also added 2.55 grams of solute. This equals 252.55 grams of solution. It is an aqueous solution, so I'm going to assume 1 gram per mil. That is very common for dilute aqueous solutions to do. That means, though, that I have 252.55 milliliters of solution, which is the same as 0.25255 liters of solution. So I can find the molarity. I have 0.0300 moles of HA in 0.25255 liters of solution. So my concentration is 0.1188 molar initially. I just figured out the initial concentration. How am I going to find that final concentration? I know the fraction dissociated. I know how much will break apart. I know the initial, I know the fraction. Now, I want you to be careful. It's not that this X is not equal to concentration. So be careful there, okay? I'm gonna erase this because I need the space here. But I know that this percent of the original sample broke apart. So if I have a 0.1188 molar solution and 0.151%, not percent, the fraction, sorry, 0.151 is the fraction dissociated. That means 0.01794 molar is the concentration that actually formed of each of these at equilibrium. Again, I found that basically 15% broke off, which was 0.151 in fractional form. So 0.151 of that 0.1188 is the amount of H3O plus and A minus I will actually form. I wrote the Ka expression here. H3O plus, A minus, and HA. My numerator, 0.01794. It is molar, but the units aren't going to matter in a second. 0.01794 for each of these at equilibrium, okay? And again, this is the fraction dissociated, so not the same exact thing, okay? It's not the molarity that has to plug in this table. This is 0.1188 minus 0.01794 for the equilibrium concentrations. So in the denominator, I didn't actually calculate it out, 1188 minus 0.001794, or 0.01794, gives me a value of 0.00319. So the Ka value here, 3.19 times 10 negative 3. Pretty big Ka value. Number 35, calculate the pH of a solution that has 0.00115 molar HCl and 0.01 molar chlorous acid. Okay, let's think about what you got here. You have got HCl, which is a strong acid. You've got chlorous acid, which is a weak acid. HCl, aqueous, goes to H plus Cl minus. If I have 0.00115 molar here, that means I have 0.00115 molar here and 0.00115 molar here. Okay? Now, I'm going to show you something, but this is not, I'm going to show you why you wouldn't do this anyway. This is not correct, okay? If I'd actually looked at chlorous acid, which is HClO2, it is a weak acid. meaning that by itself, keyword there, or phrase there, it goes into chlorous acid, or sorry, into chlorite and H3O plus. I had 0.01 molar here. By the time I solve a rice chart for this with the Ka value, I would find that my H3O plus concentration is 2.52 10 negative 7, which is incredibly small, okay? So first of all, I've got this much H plus just from the HCl. Adding this much H3O plus to it from the chlorous acid does not make a bit of mathematical difference. But I want to take it a step further and make you actually think about what's happening here. Le Chatelier's principle comes into effect. HCl is going to dissociate 100%. When that happens, it's going to flood the system with H plus ions. I have flooded the system with H3O plus ions. What does that do to this equilibrium? I've increased the product side. It's going to throw it back to the reactant side, which means that even by itself, chlorous acid would only dissociate this much, or it would only make this much hydronium. But it's going to make even less because this isn't going to break apart. It's got protons coming from another source. So the pH of the solution is going to be dependent just on the H3O plus concentration from the HCl. So negative log 0.00115, pH is 2.93. It's a pretty dilute solution of HCl, so it's not a real strong pH, but even still, because of Le Chatelier's principle, even less of that hypochlorous or the chlorous acid will actually break apart. Let's see, number 35. A mixture of sodium carbonate and sodium bicarbonate has a mass of 82.2 grams. It is dissolved in 1 liter of water and the pH is found to be 9.95. What is the percent composition of the mixture? Okay. I know you guys just love these questions. So we're going to go ahead and let X equal the grams of NaHCO3 and Y equal the grams of Na2CO3. I know that X plus Y has to equal 82.2 grams. So Y has to be 82.2 grams minus X. I know number of moles of NaHCO3 is equal to however many grams I have of the dang it, NaHCO3 times 1 mole NaHCO3 over 84.01 grams. Okay, the molar mass. So this is equal to X moles divided by 84.1 grams of NaHCO3. It's annoying to see it that way, but I mean, it's valid. And do the same thing for the carbonate. So my my Na2CO3, 82.2 minus X grams, Na2 or Na. Sorry, I'm trying to make sure I've got the right things in here. Minus the grams of NaHCO3 times 1 mole. Definitely going to run out of space here. Move this down. 1 mole of Na2CO3 weighs 105.99 grams. 82.2 minus X moles divided by 105.99 grams. It represents the Na2CO3. Now, this is where it's going to get really ugly, if it wasn't already. My HCO3 concentration, these are all in 1 liter. I just told you that this represents the moles of NaHCO3. So I know it's a 1-to-1 ratio, so that means that my X moles NaHCO3 divided by the 84.01 grams divided by 1 liter solution. I know that 1 mole of HCO3 minus is comparable, chemically equivalent to 1 mole sodium bicarbonate. And because it's divided by 1, I apologize. I actually have no idea what I was last saying because someone called and it disrupted the video. But this represents X molar. Series drive me nuts. Molar of the bicarbonate. X over 84.01 molar is representing that. And I do something very similar with the carbonate. So my carbonate concentration, I just figured out down here, 82.2 minus X moles over 105.99 grams, all over the 1 liter solution. I know that 1 mole of carbonate is present for every 1 mole of sodium carbonate. So I have 82.2 minus X divided by 105.99 grams, and that's the molar CO3 2 minus. And I realize how much students absolutely hate what I just wrote, but it's just placeholders for now. Let's go ahead and get up our rice chart. I've got, I don't think I put in the extra question. I think I put it was in the original question, but it gave me a Ka value for carbonate, and it told me the Ka for carbonate. So it's really the Ka2, if you look it up, is 5.6 times 10 negative 11. But carbonate here is going to act as a base. I'm going to have CO3, 2 minus, in water, producing HCO3 minus and hydroxide. How do I know it's acting as a base? My pH is basic. It's basic. Solution basic. Your rice chart's a mess here, just to warn you. For carbonate, we've got that 82.2 minus X over 105.99. I'm going to write a Z here for a different letter because we have X already. 82.2 minus X over 105.99 minus Z. Here I have X over 84.1 plus Z. And I have approximately no hydroxide plus Z plus Z. I know my Kb value. I can solve for it through W. So Kb is going to be equal to 1.79 10 negative 4. Kb is equal to HCO3 minus concentration times OH minus concentration times my carbonate. Again, I know it's acting as a base because my pH is basic. I know we've got a basic solution here. This is, again, a mess. X is over 84.01 minus C, or sorry, that is plus C. I'm looking at products here. And my hydroxide concentration, which I will discuss in just a sec, divided by 82.2 minus X over 105.99 minus Z. I'm going to assume Z is very small, but truthfully, I'm going to figure out Z in just a sec. How can I figure out Z? I don't have to assume X is, I don't even have to assume Z is small. I can solve for it. Z represents the hydroxide concentration equilibrium. I have the information to find that. I know that the pH is equal to 9.95, which means you can go through pOH if you want. I did not in this case. And I don't have the number. I don't have a calculator in front, so I got to write down what I already wrote down beforehand. But this means that my H3O plus concentration is 10 to the negative 9.95, which equals 1.12, 10 to the negative 10. Sig figs are here. That's two sig figs here, two sig figs here. But remember that hydronium concentration times hydroxide concentration is equal to Kw. So my hydroxide concentration is equal to 1.0 10 negative 14 over 1.12 10 to negative 5, sorry, 10 to negative 10, what I just wrote down for what I just solved. So my hydroxide concentration here is 8.93 10 negative 5. I can plug that in for Z. I don't have space to plug that in, but we're going to pretend. 8.93 10 negative 5 times 8.93 10 negative 5 minus 8.93 10 negative 5. What's going on there? Solve that mess. Again, all of this is equal to KB. Solve for X, and I get an X value of 50.4. And we probably forgot what X meant at this point because I've definitely erased it. But X is the number of grams of NaHCO3 in the sample. That means I have 50.4 grams of sodium bicarbonate and 31.8 grams of sodium carbonate, which gives me 61.3% of the sodium bicarb and 38.7% of the sodium carbonate. Okay, last question. 0.1 molar aqueous solution of scandium 3 chloride solution is prepared. What is the reactions equilibriums occurring when scandium 3 chloride ion is scandium 3 chloride is placed in water? And what is the pH of the resulting solution? This goes back to that aluminum chloride example. This was a test question. My students did not like it. I can't help if you don't like it. It was a test question. You should be able to do it. What reactions and equilibriums occur when scandium 3 chloride is placed in water? Well, if Siri would leave me alone, scandium is SC. So 3 plus, that means I got 3 chlorides. When I put that into water, it splits up into scandium ions and 3 moles of chloride ions. Remember that it is it's soluble, it's breaking up entirely. Why am I assuming that? Because I'm telling you it's an aqueous solution and I've got a concentration. I'm just going to assume it's splitting apart, to be honest with you. Remember the process of how it splits apart, how the water molecules surround the ions and support them, the oxygen supporting the cation, the hydrogen supporting the anions, etc. All of that process. You should be able to explain all that. You should recognize that chloride is going to just act as a spectator in solution because it is a conjugate of a strong acid. It is very, very stable. It is a conjugate base. It is a weak base and a very stable base. It is this piece that we care about. It is this that is acting as that Lewis acid. So the SC3 plus binds up with those 6 water molecules that it used to separate away from the chlorides. Single-headed arrow still, giving me SC, H2O6, 3 plus. It is aqueous. It's keeping the full charge of the scandium here. It hasn't added any anions to it, so it's still a plus 2 charge. Or sorry, plus 3 charge. It's still a plus 3 charge overall. This species, then in water, remember it's so positive, it's the charge to size ratio is so good for the scandium that's pulling those water molecules really, really close through the oxygen. What that's doing though, the oxygen is very attracted to the scandium, it's polarizing the bond with the hydrogen atom on one of the water molecules, and a different water molecule comes along and steals the proton off of one of those water molecules. It weakens that bond, that covalent bond, allowing a different water molecule to steal that proton. So this is aqueous plus water. This is an equilibrium. Because once it loses that proton, it can go back and steal one from one of them from another hydronium. It can steal it back. Scandium, H2O5, because I don't have 6 waters anymore. OH, because one of them got switched to hydroxide, and now it's a 2 plus charge. And it forms hydronium ion. The production of this species is what's making it acidic. So now I can figure out the pH of the solution. I'm doing that because I'm tired of writing these out, to be honest with you. If I have a 0.1 molar solution of the scandium 3 chloride, or scandium 3 chloride, that means I have 0.1 molar here, minus X, 0.10, minus X. Water's my solvent, so it's not going to change concentration. 0 plus X and X, approximately 0 plus X and X. Write out my Ka expression. Ka is equal to the concentration of that hydrated scandium ion. So H2O, I've got 5 of them there because it's already lost a proton. OH2 plus times my H3O plus concentration. SCH2O6. My Ka I'd have to give to you. In this example, I actually gave students the pKa of 4.61, which means that my Ka is 10 to the negative 4.61, or 2.5 10 to the negative 5, equal to x squared over 0.10 minus x. Solve for x, and I get an x value of 0.00158. Remember what x represents. X represents my hydronium concentration. So this is a molarity here. And my pH is negative log of that hydronium concentration. And the value is 2.80. Congratulations, we have finished the additional practice for this